Alright, so now we are ready to talk about prediction using noise-free observations. So assume that we have training set. My D is like this, and it's just xi and fi, and we have just n number of data points. So the joint distribution has the form f star drawn from a normal distribution mu and mu star, and the covariance is just k star, k star star, k star transpose. And k is just k of x and x. K star here is just k of x and x star. And k of star star, this guy, is just k of x star and x star. Now, by the rules of a previous lecture of my playlist for Gaussian processes, you can see that the posterior P of f star condition on x star, x and f is equal to normal of f star, mu star, and sigma star. And the mu star is equal to mu of x star plus k star transpose k minus 1 f minus mu of x. So now you understand why the first lecture, that lemma that I started off, was so important. Because you can just read off that and you see that you know why this has happened. Now I want to introduce squared exponential kernel, which is called SE. So we have sigma f squared, which controls the vertical variation, times e to the minus 1 over 2L squared, which controls the horizontal length scale, x minus x prime to the 2. So this kernel is very popular, although, for example, for periodic problems, the one that you have seen, so for example, in solar sunspot, that I've put the links on my YouTube profile. So you should use periodic kernel for that kind of problem. And it all depends on the kernel. Finding a kernel is a problem of statistics, which is beyond machine learning. And that's why statistics is much more deeper than machine learning or anything else like deep learning and those things. And so the prediction using noise observation is just you use f of x as before, but now you add epsilon. Your noise is like mean 0 and sigma y2. And by this, you have added one more hyperparameter. But no problem, because we will solve it through several different ways, either point estimator like maximum likelihood estimator, maximum posterior, or if you like to see the uncertainties around that, which I love, I use Monte Carlo, and particularly Markov chain Monte Carlo, such as Metropolis Hastings, Gibbs sampling, and those stuff. And so the covariance of y of p and y of q is just k of xp and xq plus sigma y squared delta pq. And the covariance of y condition on x is equal to k plus sigma y squared in, which we write it ky. So this symbols is just for simplicity we write like that. And the joint density y f star, the joint density, is drawn from the normal distribution of ky, k star transpose, k star star. So with this in mind, we are ready to do a posterior predictive density, which is, we can write it as f star condition on x star and x and y, which is the normal distribution f star, mu star, and sigma star. And this mu star is just ky minus 1y, and this sigma star is just, so it's like the same thing that I used for not using the noise, but so you see an extra term. K star, because ky, as I said, this ky is just k plus sigma y2i. So this term is just new. The only new term that we added is just this. So in the case of a single test input, we have p of f star, x star, a little bit simplification because it's just a single test input, not a vector of test input. So we use f star condition on k star transpose ky minus 1 ky, and the covariance is just k star star minus k star transpose ky inverse k star. And the posterior mean, which is f star bar, so you see that the mean of that, what is the mean of that? It is k star transpose ky minus 1. But the matrix form, the algebraic form is just equivalent, so you can write this as, so it is the same thing as this, but now I want to write it as a sum of some basis functions. Well, you have seen my lectures on reproducing kernel Hilbert spaces and see why and how everything is connected to each other, like your memories inside your brains. And you know your brain is like a Markov chain. And that's why you remember things, you can record things. And the future of cognitive science and machine learning should be based on Markov chains on the general state space. And so alpha is just, this is a vector, and ky minus 1y. So the ith entry of that is just the coefficient of this basis. And it is like a kernel density function. It is related to many different theories in mathematics, as you see. So now what is left with is what we should do is in fact estimating the kernel parameters, and so we maximize it by marginal likelihood, for example. The probability of y given x is equal to probability y given f and x, probability of x given x d of f, and f of 0 and k, and the probability of y given f is the ny yi fi sigma y squared. And so we can assume that they are like separated like that. And the marginal likelihood log of p of y condition on x, and the log of because normal distribution is exponential, so if you just take a log, everything is simplified. This is the main motivation that people use Gaussian distributions in general, because the marginal likelihood in those things is very simplified. Of course, I will show you why it is not that good, because if you write this is called data fit term. Data fit term. So in your company, you should talk about these things, because it's a trade-off between this term, which is called model complexity. Model complexity term. And minus n over 2 log of 2 pi. So it doesn't matter because it's constant. So there is a trade-off between this data fit and complexity model. And I will explain here that, for example, consider that SE kernel that I said, squared exponential kernel that I said, which is sigma f2. So we fix sigma f2 and let the other hyperparameter to vary. So this is the next hyperparameter. So we can define this in terms of length scale, which is log of p of y condition on x and L. So if L is small, if this L is small, so you observe that y transpose ky inverse y is small. So fit will be good, fit is okay, but bad model complexity. It's like real life. You receive something, you lose something else. So it's a trade-off. Log of k of y. For example, you're very talented and genius, but you're in a third world country like Iran, and so there is a trade-off with everything. And for large L is large, fit will be poor. Fit is poor. And the model complexity is low, and so your K, in your K matrix, most of them are just 1, and the log of ky is small. So let the hyperparameters theta to be L and sigma f. So you just take derivative with respect to your hyperparameter, log of p y condition at x. So this is just y transpose ky minus 1 ky inverse y minus 1/2 trace of ky inverse. So this is equal to 1/2 trace of alpha transpose minus ky minus 1. And this is just the order of n2 time per hyperparameter. And this is a problem because it takes order of n cubed time to compute ky inverse. But you know from computer science that you don't care about this because this one is much higher. So in general, order is n cubic time. So order of complexity is n cube, and now we use the standard gradient-based optimization. Or if you don't like, if you think it is not good, you can use conjugate gradient or your favorite advanced mirror descent algorithm. So the challenge here is just really the objective is not convex. So local minima is a problem, like many non-convex problem in the world. And I've written 2 papers about non-convex optimization. If you check my Google Scholar, you will notice that how we can deal with non-convex function using some successive approximations and some techniques. But in general, you should avoid non-convex problems, because if you can't formulate your problem as a convex problem by just doing some creative formulation, so why do we need non-convex things? So we should avoid non-convex stuff as much as possible, because it affects your computations. And at the end of the day, your computational complexity is the bottleneck for your algorithm, especially if you're working on Microsoft or Google. And so using the Bayes rule, I want to write P of f condition on y, which is the posterior over function, to be the probability of y condition on f times the probability of f, and P of y f P of f df. So for unseen inputs, P of the probability of f star condition on y is equal to the conditional GP prior, which is P of f star condition on f, times your posterior over function that I said, P of f condition on y d of f. So this is just this. And now this term P of f star condition f is just the normal distribution f star condition on your mean is k f star f k f f minus 1 f, and your covariance is just k f star minus k f star and f k f and f inverse k f star and f transpose. So the prediction of values y star is P of y star condition y is equal to the probability of y star condition f star times for unseen inputs that I said is f star condition on y and df star. So when likelihood is Gaussian, everything is tractable. Okay, so the posterior Gaussian process, it depends on the values of the kernel parameters theta, as well as the likelihood parameters alpha. This is related to noise variance. So the GP prior P of f condition of theta. So this alpha and theta, so these are hyperparameters of the Gaussian process model. So a common practice is maximizing the marginal likelihood, which is the probability of y condition and alpha and theta, which is the integral of P of y condition on f and alpha, P of f condition of theta df, and continuous optimization over alpha and theta will solve the problem.